What's up? Let me ask you a question. What do you think is the effective capacitance of this entire system? At first you might want to say that the capacitors C1, C2, C3, C4 are all connected in series with each other. But then that would be wrong, because the effective capacitance can only be calculated provided I give you 2 points. Effective capacitance between point A and point B is not the same as the effective capacitance between point A and point C. You must always think about the 2 points across which you are calculating the effective capacitance. You change the 2 points and the effective capacitance can change, and that's the whole idea behind this problem. So in the first example, we have been asked to calculate the effective capacitance between A and B, and we have connected a voltage supply of 10 volts, and because of that we're going to find out what's the charge on every single capacitor. So let's begin with the first one. So here's our solution. This is our first one. So let's redraw that circuit. Here is our circuit, and since we are connecting the battery across A and B, I'm going to draw 2 LEDs over here. It's going to be LED number 1 and it's going to be a LED number 2. It's a wire. Think of this as a wire. Now this is going to help us understand exactly what the effective capacitance is. Let's begin with this question. Do you think C1 and C2 are connected in series with each other? The answer is no, they're not connected in series, and I'll show you why. Because if you were to take a very tiny charge, say a charge Q, and if you were to make this charge flow from C1 to C2, do you think all of that charge would flow this way? The answer is no. Some of the charge would split up and they would go in this direction. So you see, all the charges don't go from C1 or C2, or they don't have to go, and because of which they may not end up with the same charge. If they don't end up with the same charge, then they are not in series with each other, because that is the definition of series capacitance. And therefore C1 and C2 are not in series with each other. And the same thing goes for C1 and C4. They're not in series, because again you will notice that the charges will move from C1, a part of it can go to A, to this wire, into the battery, and some of it might go here. Again, they will not end up with the same charge. On the other hand, notice C4 and C3 are in series, because if you were to send a very tiny charge Q all the way from here to here, then notice that all the charge has to go through this plate of the capacitor. Therefore C4 and C3 will always have the same charge at electrostatic equilibrium, and same is the case with C3 and C4. So this tells us that the capacitors C2, C3 and C4 are in series with each other. So let's write that down. Here we have our solution. C2, C3 and C4 are in series with each other. And since they are in series with each other, we can find their effective capacitance. Well, the effective capacitance 1 over Cs is just going to be 1 over 6 plus 1 over 6 plus 1 over 6. Well, that's 3 over 6. That makes the effective capacitance Cs to be just 2 microfarad. And so the next step will be to take this system over here. To take this system over here, system of 3 capacitors, and we're going to replace them with 1 single capacitor. That's what we're going to do now. All right, and we're going to keep the rest of the circuit as it is. Okay, so here is our new circuit, new equivalent circuit. Here we have it. Here is first plate. This is 6 microfarad, and this is not changing. Okay, this remains the same. But what does change is the bottom part. I'm going to replace all the 3 capacitors with 1 single capacitor, and that single capacitor will be 2 microfarad. And let's not forget this points A and point B, and let's keep on drawing those wires, because those wires are going to help us and tell me correctly whether they are in series or parallel. And now you can notice that these 2 capacitors are connected across each other. There's absolutely no connection in between. In other words, they're going to have the same voltage. Notice at this point is A and this point is B, but the same point over here is B, and the same point over here is A. Therefore, these guys are in parallel with each other, and when the capacitors are in parallel, they just get added up. And therefore, we're going to replace these two capacitors now, these two capacitors, these two, with one single capacitor. And that single capacitance will have the equivalent capacitance of 6 plus 2, that's going to be 8. All right, and so we're going to have one single capacitance, or one single capacitor of 8 microfarad. And here are our points A and points B. All right, and don't forget the leads are still there. And now eventually I'm going to connect that battery. Here's our battery, and that battery was given to us and was told that it is 10 volt. So let's put 10 volts over there. It's going to be, I'm going to use red for voltage. So this guy is 10 volts. All right, now that we have one single capacitance, we can now find out what's going to be the voltage on this capacitor at equilibrium, and that voltage is just going to be 10 volts. So I'm just going to put that voltage over here. This is going to be 10 volts. And what's going to be the charge on that capacitor, this equivalent capacitance? Well, that charge is going to be Q is equal to, what's wrong with this? Okay, the charge Q is going to be equal to, remember the formula, Q equals C times V, and therefore the charge Q, it'll just be 8 times 10, and that's going to be 80 microcoulombs. So we have found the charge and the voltage on this capacitor, but that's not what I want. I don't want the charge on the equivalent capacitance. My goal is to calculate charge on every single capacitor. And so the trick that I'm going to use now is I'm going to start going backwards. So I'm going to go back from this circuit to this circuit. That's where I came from. And when I go back, I'm going to ask myself, how is this capacitor splitting up? If it's splitting up in parallel or series. If it splits up in series, they're going to end up having the same charge. And then I can calculate the voltage on each one of them. If they split up as parallel, then they're going to have the same voltage, and then I can calculate the charge on each one of them. In this example, this capacitor over here, is splitting up as two parallel capacitors, as you can see over here, and therefore they're going to have the same voltage, and therefore this guy is going to end up with 10 volts, and this guy is going to end up with 10 volts. But if the voltage, so I'm going to put one line over here to differentiate this. All right, so if you know the voltage, we can calculate the charge. So the charge on this capacitor is going to be 2 times 10, that's going to be 20 microfarad. The charge on this capacitor is going to be 6 times 10. That's going to be 60 microfarad. I'm going to write 60 microfarad over here. And notice that makes a lot of sense because the charge 80 got split up as 60 and 20. Again, notice this is not our final answer, so we're going to go back. We're going to go back up now. We're going to ask ourselves, oh, look, this capacitor is done. We already know the answer for this guy, this capacitor. So let's write that down. So this guy is going to end up with 10 volts, and it will have 60 microcoulomb. That is not going to change. However, notice this one single capacitor was actually due to 3 capacitors. I hope you can see that. This one single capacitor was due to 3 capacitors, and therefore, and they're in series with each other, hence they're going to end up with the same charge. And so each one is going to have a charge of 20 microfarad, sorry, not microfarad, microcoulomb. It's supposed to be microcoulomb. Here will be 20 microcoulomb, and here will be 20 microcoulomb. And now that we know what the charge is, we can calculate the voltage on each one of them. The voltage is going to be just 20 divided by 6. 20 by 6 is what? 3.7 volts. So each one is going to end up with 3.7. Here is 3.7, and here is going to be this is very crowded, 3.7 volts. Anyways, we have solved our problem now. Okay, so that is solution to the first question. All right, let's now find out the solution to the second question. The second question is calculating the effective capacitance across A and C, and then figuring out the charge on each capacitor and the voltage on each capacitor. If you have followed me in this, you should be able to do this yourself. So I really encourage you to pause this video and try this out yourself. Alright? Alright, so here we have it. We have redrawn this circuit over here, and this time we're going to consider case number B. And in case B, our battery is connected across A and C. Okay, let's ask ourselves, which two capacitors are in series and which two are in parallel? This time you can notice that C1 and C2 are directly in series with each other because they're directly connected to each other. So C1 and C2 are in series. C3 and C4 are in parallel with each other, and therefore let's write down the equivalent circuit because of that. So this is going to be equal to, I'm going to make one capacitor over here. So I'm going to put one single capacitor. These two capacitors, C1 and C2, I've put it over here. That's 6 and 6 in series, and that is just 3 microfarad. This is also 6 and 6 in series, which is again 3 microfarad. And let's not forget our leads, our wires. Our wires are over here. Now notice that these two capacitors are connected across the same points. This is connected across A and B, and this is connected across A and D, but D, C and B are not exactly the same points because there is no capacitors in between each other. So C, D and B must be at the same potential, and therefore these guys are just parallel with each other, and hence we can now redraw a new circuit with just one capacitor between A and B, or A and D, or whatever that is, just one capacitor, and that capacitance is going to be the parallel value for 3 and 3. That's going to be 6 microfarad, and this will be our point A and point B. And let's draw our wires. This is going to be our wires, and wait, this time I'll draw the wires down, and here we are connecting a 10 volt power supply. So now here is our 10 volt power supply. Oops, I'm going to put red as voltage. So 10 volts. Since this power supply is 10 volts and it's connected across one capacitor, just like before at electrostatic equilibrium, this guy is going to end up with 10 volts of voltage. And so the charge on the capacitor is going to be 10 times 6, so the charge is going to be just 60 microcoulombs. You know the exercise now. All we do now is go backwards. When we go backwards, we ask ourselves, hey, how did we get this 6? Oh, we got that 6 because of parallel capacitance. Well, then they're going to have the same voltage. So this guy is going to have the same voltage as 10 volt. And then this guy is going to have the same voltage as 10 volt. And therefore, they're going to have each of them charge of 30 microcoulombs. I hope you can see that. 3 times 10. So that's 30 microcoulomb here. And that's 30 microcoulomb over here. Now we go backwards and we ask ourselves, hey, how did we get this 3 and this 3? And it turns out they got that because of the series capacitance. And hence, they're going to end up having the same charge. 30 and 30. And so same thing over here, 30 and 30. Since they're going to end up having the same charge, they will end up having the voltage, which can be calculated. It's going to be 30 divided by 6. That's going to be 5. So we're going to end up having 5 volts. In fact, each one of them is going to end up with 5 volts. Alright? So I hope this has cleared some of your... I hope I have helped you understand how to solve capacitance in series and capacitance in parallel. Alright, so see you next time. Stay tuned.